Let's start with a really wild thought. What if the most fundamental thing we all experience, the passing of time, isn't just a passive clock ticking in the background? What if it's the actual, active force that's building our entire reality? Today, we're diving into a really fascinating idea called the Vacuum Cascade Model that says, yeah, that's exactly what's happening.
We usually think of time as this straight line that we're all traveling on together. But this model, it wants us to imagine something way more profound. What if time is a physical thing, like a field, that can actually flow and compress and even push on things, literally shaping the cosmos as it goes?
And that really gets to the heart of it. This quote nails the whole idea behind the Vacuum Cascade Model, or VCM for short. It's saying that time isn't just a static backdrop for the show. No, time is the show. It's the main actor, constantly creating the space-time curvature we feel as gravity and driving the expansion of everything.
So how in the world does that actually work? How can time itself push or pull on anything? Well, the model says it all boils down to one key concept, something called the temporal gradient.
Okay, so this is where things get really interesting. This idea of a temporal gradient actually builds on what Einstein already told us. We all know from general relativity that massive objects warp spacetime, right? Well, VCM says why. It argues that the presence of matter literally slows down the local flow of time, and that creates this gradient, a difference in the speed of time between that spot and the space around it.
So you've got to picture this chain reaction, right? First, you have matter. That matter slows down time right around it. This creates that temporal gradient. Now think of that gradient like a low-pressure zone in the weather. The surrounding, faster-flowing time naturally pushes inward toward that slower region. And that push is what we feel as the curvature of space, which is, of course, gravity. It's a constant dynamic process.
Okay, so you might be thinking, this is a really cool idea, but does it actually solve any real-world problems? Well, the people behind this model argue that it offers some pretty elegant solutions to some of the biggest head-scratchers in cosmology today.
So let's talk about the Hubble tension. This is a big one. When astronomers look at the universe close to us, using things like supernovae as mile markers, they get a certain speed for how fast the universe is expanding. But when they look at the afterglow of the Big Bang, way back in the early universe, they get a different, slower speed. And that 9% gap, that's a huge headache for cosmologists. It means either our measurements are off, or there's some brand new physics we just don't get yet.
Now, to understand the VCM solution for this, you need to know a little secret about our cosmic address. It turns out that our galaxy, the Milky Way, is hanging out inside this colossal cosmic bubble called the KBC void. And it's huge. We're talking 2 billion light years across, and it's way less dense with galaxies and stuff than the rest of the universe on average.
And this is where the VCM explanation has its aha moment. It suggests the Hubble tension isn't some universal mistake, it's a local effect. Think about it. Because we're in this less dense void, there's less matter around to slow down time. So, according to the model, time right here flows just a little bit faster than the cosmic average. Our clocks, our telescopes, the supernovae we're measuring, they're all operating in this temporal basin, which makes the local expansion look faster. It's not an error, it's all about where you're standing, or in this case, where you're floating in the cosmos.
And it doesn't stop there. The model also takes a fresh look at dark energy and dark matter. In this picture, dark energy isn't some weird, mysterious substance. It's just the natural tendency of time to speed up its flow in the huge empty voids of space, which pushes everything apart. And dark matter? Not some invisible particle. It's more of an illusion, an effect that happens in really dense areas where the flow of time gets bogged down, creating an extra gravitational pull that we've mistaken for some kind of unseen mass.
All right, if you thought that was wild, wait until you hear what this model says about stuff, the very nature of matter itself. If time and the vacuum are this dynamic, where does a solid rock or a planet even come from?
So instead of thinking about fundamental particles as these little tiny marbles, VCM suggests that matter is more like a sound wave that holds its note. It's a stable vibration, a standing wave, in this dynamic field of time and vacuum. Think of it like a perfectly held note on a guitar string that just sustains itself.
And here's how that cascade works. The flow of time is constantly creating these little ripples and pressure changes in the vacuum. Most of them just fade away. But every now and then, some of these ripples hit a perfect frequency,
and they lock into a stable, self-sustaining pattern, a resonance. And that stable wave, that resonance, it pushes back against the flow of time around it. That resistance to being moved, well, that's exactly what we call inertia, which gives us mass. So in this view, matter is literally a knot in the flow of time.
Okay, I know what you're thinking. This all sounds incredibly abstract, almost like philosophy, but here is the absolute best part. The vacuum cascade model isn't just an idea. It makes a concrete, testable prediction that we could actually check out with technology we have today. So how do you test time itself? Well, the trick is to isolate the one specific effect that this VCM theory predicts, but that general relativity doesn't. And to do that, you need clocks that are so mind-bogglingly precise, they can measure a tiny little hiccup in the flow of time caused by nothing more than the density of the rock right under your feet.
And the way they propose to test this is just so clever. You take two of the world's absolute best clocks, you sync them up perfectly. Then you carefully adjust their height difference so that the effect of gravity that Einstein predicted is exactly the same for both of them, completely canceling it out. Then, you put one clock deep underground, surrounded by dense rock, and you leave the other one up on the surface, surrounded by plain old air. Every known effect is canceled out, except for one.
And this is the whole ball game right here. VCM predicts that the sheer density of the matter packed around that underground clock will have its own tiny, separate influence on the flow of time, an influence that has nothing to do with gravity. It means the underground clock should tick just a tiny, tiny bit differently from the one on the surface.
And here's the number they're looking for. The predicted difference is about 1 part in a quintillion. That's a 1 with 18 zeros after it. It means for every quintillion ticks of one clock, the other would be off by just 1 tick. I mean, wow. A decade ago, trying to measure something that small would have been a joke. But today, our best optical clocks are actually precise enough to spot a signal that tiny. It's incredible.
Now, just imagine for a second, if this experiment were actually run, and they found that exact signal. The implications would be absolutely staggering. It would be the first real, direct proof that time isn't just a coordinate on a map, but a living, dynamic field that actually responds to the matter around it. It would be a huge leap toward a completely new way of understanding our universe.
And that leaves us with this one kind of mind-blowing final thought. This whole model suggests that time is the architect of the universe. So if we can finally understand its rules, if we can prove that matter really does shape the flow of time, it raises an incredible question for our future. Could we one day learn to become the architects too?